Okay, number 7, let's get going. We have 3 functions, ln, sine, and x to the 0.5. 3 functions, 2 chains. We are taking the natural log of the sine of x to the 0.5. So the outermost function is ln. So 6 comes along for the ride. The outside function is ln. The inner as is everything else. So those 2 functions are the inner as is, the sine of x to the 0.5. All right, this is still a composite function. There are still 2 functions here. So that means we go again. Chain number 2. The sine of x to the 0.5, this is our outside function. So chain 2, the outer is sine and the inner is x to the 0.5. All right, there's our 2 chains. So we get going. Remember, on the first chain, we only do the first 2 steps. So for v prime, the derivative of the outer, 6 comes along for the ride first. Don't forget that. I'm going to make it a fraction. But the derivative of ln is 1 over x, and we always write that as 1 over something. We need a blank set of parentheses whenever we take the derivative of the outer. Second step, we plug the inner as is in right there. Alrighty. So the sine of x to the 0.5. So that is my first chain right there. Chain number 1. Only the first 2 steps, and now we start over with chain number 2. Right here, the derivative of the outer, the derivative of the sine is cosine. So we put cosine, blank set of parentheses, and make everything a fraction, keep it organized, so simplifying is easier at the end. Second step, we plug in the inner as is right here. So inside that blank set of parentheses, x to the 0.5. And then don't forget, on the last step on the last chain, we need the derivative of x to the 0.5. So that's a power rule. So that's going to be we have to multiply the exponent times the coefficient, so that's going to be 0.5x. And then if we subtract 1 from 0.5, we get negative 0.5. So 0.5x to the negative 0.5, all over 1. So this is my second chain, all 3 steps. So when you're doing a double chain, on the first chain, only the first 2 steps. Derivative of the outer, 1 over something, inner as is, sine of x to the 0.5. Start over. Second chain, all 3 steps. Derivative of the outer, cosine, plug in the inner as is, x to the 0.5, multiply everything by the derivative of the inner, 0.5x to the negative 0.5. All right, when we simplify this, multiply tops and bottoms. On top, we have 6 times 0.5. That gives us a 3 out front. All right, don't forget, we still have an x to the negative 0.5. And we still have cosine of x to the 0.5. That is my numerator. My denominator is simply right here, sine of x to the 0.5. All right, so there is our simplified answer. Now we could recognize right here, the cosine over the sine is the same as the cotangent. All right, so we could write that like this. We still have 3x to the negative 0.5, but then it would be times the cotangent of x to the 0.5. All right, so that is another possibility right here. All right, try to go through that one on your own. That is a tricky one. Number 8, be on the lookout for when you see E and ln right next to each other. Those are inverses of each other. They cancel each other out. And you are only left with what's left up there. So when we simplify this, we get x. And the derivative of x is equal to 1. Number 9, we want to recognize that this is an exponential function. The variable is in the exponent. It is an exponential function, base 3. So we use the formula. Remember, if you have an exponential function of any base, to take the derivative of that, you rewrite that function and you multiply it by the natural log of the base. All right, so that's your derivative flashcards that you just need to know. So to take the derivative of this function, we rewrite the function as is, 3 to the x, and we multiply it by the natural log of the base 3. And that is as far as you can go. You just follow the formula. Alrighty? Number 10, this is a composite function. We have the variable is in our exponent, so we know that that is an exponential function, base 1.6. And then the second function is the cosine of x. Whenever your variable is in the exponent, the base is always the outer function. So our outer function is 1.6 to the something. All right, again, when your variable is in the exponent, the base is always your outer function, and we write it like this. Our outer function is 1.6 to the something. Then my inner function has to be the cosine of x. All right, to take the derivative of this, I'm just going to call it y prime. To take the derivative of this, remember, we have to go and use the formula that we just reviewed up in number 9, right here. All right? The derivative of an exponential function of any base. We follow this. We have base 1.6. So that derivative, looks like this. We rewrite the function as is 1.6 to the something times ln 1.6. This whole thing is the derivative of our outer function 1.6 to the something. Second step, I plug in the inner as is right there inside that blank set of parentheses. That's why every time you take the derivative of the outer, you need a blank set of parentheses. This is my inner function as is. And don't forget, we need all 3 steps. We need the derivative of the inner. The derivative of the cosine is negative sign. I would put it in parentheses so it doesn't look like subtraction and confuse you. That is the derivative of the inner function. All right, really the only thing we can do here is we make sure that we get that negative 1 out to the front. So when we simplify it, it's just negative 1.6 to the cosine of x times ln 1.6 times the sine of x. All right, and if you want, you could put these in parentheses to clean it up a little bit, but this is your final answer. That's as far as you can go. That's a tricky one. Please make sure you're going through these on your own. Number 11, remember that this is a notation for a second derivative. So you have to find the first derivative, simplify, and then do it again. This is a typo right here. It should be, I'm going to rewrite that. All right, our function should be just ln of x to the 5th. All right, so my outer function is ln. My inner function is x to the 5th because we're taking the natural log of x to the 5th. All right, so the first derivative, y prime. The derivative of the outer, the derivative of ln is 1 over something. So that is the derivative of the outer. The second step, we plug in the inner as is right inside that blank set of parentheses in the denominator. That's my inner as is. And now we multiply everything by the derivative of the inner. And the derivative of x to the 5th, using the power rule, is 5x to the 4th, and put it over 1. When ln is your outer function, make everything a fraction. It's much easier to simplify. So now we must simplify before we go take the second derivative. All right, so to simplify, we just multiply tops and bottoms. All right, on top, we just have 5x to the 4th. On the bottom, we have x to the 5th. All right, now when we simplify that, we can combine, or we can simplify my x's. All right, so the 5 stays in the numerator. All right, don't put that 5 anywhere else. But right here, if we have 4 x's on top and 5 x's on the bottom, there is an extra x in the denominator. So there is my first derivative right here, 5 over x. So now we go to the second derivative. All right, our first derivative is 5 over x. The easiest way to take the derivative of that is not to use the chain rule, because the chain rule obviously doesn't work on a fraction. So we're going to get rid of this. We don't need inner and outer functions at all. We're just going to rewrite this. That's the same as 5x to the first even 5 over x to the first, even though we don't write it. So when we bring that up to the numerator, that exponent becomes negative. It becomes 5x to the negative 1. Now we can use the power rule for the second derivative. All right, so the second derivative is simply negative 5x to the negative 2. Or we can practice getting rid of those negative exponents. We can put it as negative 5 over x to the positive 2. When we move this back downstairs, that negative 2 becomes positive 2. So either of those are acceptable. They are equivalent. Number 12, this is another symbol for second derivative. You have to know the notation in calculus. All right, so my outer function is e, because when your variable is in the exponent, the base is always the outer function, so e to something, and my inner function is negative 0.7x. All right, first derivative, y prime. The derivative of the outer is e to something. The inner as is goes right in there, so that becomes negative 0.7x, and then we multiply everything by the derivative of the inner. The derivative of negative 0.7x using the power rule is just negative 0.7. I'm going to put it in parentheses so it doesn't confuse me and look like subtraction. You have to simplify before you can take the second derivative. To simplify, that negative 0.7 goes out front. So my first derivative is negative 0.7 e to the negative 0.7x. Okay, now we take the second derivative. This negative 0.7 comes along for the ride. My outer function is e, and we write it as e to something. My inner function is negative 0.7x. Very similar to the first derivative. So when we take the second derivative, y double prime, negative 0.7 comes along for the ride. The derivative of the outer, the derivative of e to something, is e to something. The inner as is, I plug in right there. Negative 0.7x, and don't forget the last step, the derivative of the inner. The derivative of the inner, using the power rule, is negative 0.7. Put it in parentheses so it doesn't look like subtraction. To simplify, a negative and a negative becomes a positive out front. Let's see, 0.7 times 0.7 gives us a fun 0.9. So positive 0.49, and we still have e to the negative 0.7x. So there is our second derivative. There you have it. Okay, finally, number 13, we are given the derivative right here, y prime, and we have to go backwards and find the original function. Now, looking at this, this is a composite function. You have two functions, e and 2x. So in order to get this derivative, we had to have used the chain rule. So we're undoing the chain rule. All right, so when you're undoing the chain rule, the first thing you want to do is try to figure out, what do you think the outer function was and what do you think the inner function was? Well, this looks like the derivative of the outer, e to something. So we know that my outer function had to have been e to something. All right, this looks like my inner as is, e to the 2x. So it looks like my inner function was 2x. So that's the first thing that you want to do. You want to try to figure out what you think the outer and inner function is. So I think my original function is e to the 2x. Now, go off to the side and check. Take the derivative. All right, that is how you check your antiderivative. You check the antiderivative by taking the derivative. So let's go here, take the derivative of this. All right, y prime. The derivative of my outer, the derivative of e to something is e to something. My inner as is would go right here, 2x. And the derivative of the inner would be 2. I'm just going to put that in front. So when I take the derivative of this, I get 2e to the 2x. But I need this. So what can I do to 2 to make it become a 12? Well, I would just put a 6 out front. Now when I take the derivative of this, the 6 would come along for the ride. The 6 times the 2 would give me the 12. So there is my antiderivative. Remember, on the end of every antiderivative, we put plus c. So there is my antiderivative, 6e to the 2x plus c.